Hello everyone. Today we are going to discuss about programmable logic that can be designed using computational logic. In other words, we would like to learn how to design a generic logic which can be used to design any logic. Programmable means that we can program it once chip has been fabricated. So once a VLSI chip or application specific chip has been fabricated, then you cannot do any change in the logic. But what we would like to use that particular chip, we would like to mimic that any logic using that particular chip. To understand this, the gravity of this question, that how can we design any logic which is programmable, or any logic which any circuit which can behave like any other logic. So to understand this gravity, let's ask one question from ourselves, that if we want to create an n variable function, how many distinct possibilities are there? So I'll repeat this question, that I want to design an n variable function. So how many such functions, how many different distinct such functions are possible? Okay, so to understand this, one thing which we can start with is that if there is a function with n variables, then certainly we can design all of these functions using truth table. So my truth table will have 2 to the power n entries. So this is my starting point of my thinking. So that if a function I want to design, it will have 2 to the power n entries. Now what is a function? So we have understood that a Boolean function in a standard form can be represented as sum of mean terms or product of max terms. So let's consider the first one, sum of mean terms. Now each entry in this truth table represent one mean term. In a function, all of these mean terms or a particular mean term could be present or could be absent. So from that perspective, then each of this, because each of this mean term could be present or absent in my function, or its output could be true or false. So in that way, the total number of possibilities would be 2 into 2 into 2 up to 2 to the power n. So I can write it like this, 2 into 2 into 2 up to 2 to the power n. So essentially the total number of such possibilities would be 2 into power of 2 into power of n. So how big that number is? Let's say if number of variables are 2, distinct possibilities are 2 to the power 4, only 16. Now if the number of variables are 4, then the different possibilities of different functions being possible is 2 is to power 16. From where 16 came? Because 2 to the power 4 is 16. So total number of truth table entries in a 4 variable function would be 16. And because all of these entries could be present or absent, so total number of functions which are possible is equal to 2 to the power 16, which is approximately equal to 64,000. So if I want to design a function of only 4 variables and I want to I have to have either all these 64,000 possibilities, so that I can pick and choose that this is the function I would like to design, or I have to design something which is generic, so that I can say that this particular generic unit can implement any function, any of these 64,000 functions of 4 variable, which has 4 inputs. Any of those 64,000 functions can be implemented, but yes, only one at a time. This is what a programmable logic would be, and this is what we will see in this lecture. Now, but before this, my mind is still not clear that how is it possible that there would be 16 such distinct functions just with the 2 variables. So let us see in detail with the example that yes, is it actually possible or not. So now what I do is I'll try to write all possible truth tables. So how do I write all the possible truth tables? So essentially, how many entries would be there if the number of variables are 2? Truth table entries would be 4. Okay, so one truth table entry would be corresponding to a equal to 0, b equal to 0. Other entry would be corresponding to a equal to 0, b equal to 1. And similarly, a equal to 1, b equal to 0, and a equal to 1, b equal to 1. So there are the four entries in my truth table. Now what I am trying to do, I am trying to enumerate all the possibilities with this 4 output. So essentially each row in this table correspond to a different function. So this is one function where my output, my function f, has all the outputs are corresponding to all the truth table entries, all the outputs are 0. Similarly, this is the other combination where when a is equal to 0, b equal to 0, output is 0. When a equal to 0, b equal to 1, output is 1. When a equal to 1, b equal to 0, output is 0. A equal to 1, b equal to 1, output is 1. So if you see this table carefully, then it is nothing more than counting from 0 to 16. So this is 0 0 0, 0 0 0 1, 0 0 1 0, 0 0 1 1, so on so forth. So I have enumerated all the possibilities with these 4 outputs. Now the second question also came immediately, that will all these functions, we are saying that there are 16 possibilities, will these 16 possibility make sense? Are they actually distinct? Interestingly, for this 2 variable case, they are not only distinct but they also make different logical sense. So for example, if all the output, so my truth table output for all these combinations are 0, so that means I can say this function is false. F is always going to be 0. Similarly, if first 3 are 0, then and it is 1 only if a equal to 1, b equal to 1, I can say it's actually a truth table for AND gate. Now similarly, if for this particular combination I can say it is a and it with not of b. So if both of these two are a, these two are 1 and these two are 0, so that means it actually represents it is a. So similarly, you see all of this b and not of a or b XOR a or b nor x nor not of b. So all of these are meaningful combinations. Correct. So these are the different 16 combinations which we can create using 2 variables. If the number of variables are more, then the number of combinations will also be more. So for example, as we said in our previous slide, if number of variables are 4, then 64,000, little more than 64,000 combinations or functions, distinct functions can be created based on what the truth table is. Now yes, so this is the premises of this lecture. So now let's take a small detour and we'll first understand what is a ROM, read only memory. So although we have seen in one of the previous lecture, we have done some of the exercise or design exercise using memory, so we are trying to repeat here, but the question here or the topic which we are trying to understand is read only memory. So that memory which cannot be written but can only be read. Okay, so such a memory will have will give input as an address, and there would be all those contents at those addresses, and when address is given, then bits stored at that particular address would be returned. Okay, so since I am using word bits, so that means there is a possibility that more than one bits are stored at that particular address. So we call the number of bits that are stored at single address is called word. Word could be combination of 1 bit, 2 bit, 4 bit, 16 bit, 32 bit, 64 bit. You can also ask that why I am only saying the number power of 2. Actually, word could be 24 bits also, it could be 23 bits also, but usually it is power of 2, because it in the binary word it helps us in a lot of computation. It helps us in alignment of addresses, bits. Okay, so because computation become easier when it is power of 2, so that's why most of the time word or the number of bits which are stored at a particular address is power of 2, but not absolutely correct. So it could be non power of 2 also in some specific cases. Okay, so what is inside ROM? That's what we call the total number of memory cells, total number of content. So if n is the number of bits in my address and word size is m bit, then I can say the total content, total number of memory cells is going to be 2 to the power n into m bits. At every address, how many bits are stored? M bits. And how many such addresses are there? If the address bit, number of bits in the address is n, the total number of addresses would be 2 to the power n. So 2 to the power n into m would be the total memory cells which are present in this read-only memory. Now, what could be sizes? So it's usually when you see memories, you see it is written as 1 kilobyte, 2 kilobyte. It's again usually power of 2, 1 kilobyte, 2 kilobyte, 512 kilobyte, 4 megabyte, gigabytes, terabytes, petabytes, exabytes. So but when we are writing here, we are saying 2 to the power n into m. So where is this m? So m means it's usually contained inside this byte information. So for example, there could be 256 kilo addresses into 32 bits, then it will form 1 megabyte. Okay, so similarly it could be the other way around also. So there could be 1 m addresses and each word size is 4 bit, then the size would be 5112 kilobyte. Okay, so given this background on read only memory, then I want to design it. Now let's say I want to design something like 8 into 4 bit memory. So the total number of locations are 8, and on each location 4 bits are stored. Now such a memory can be represented using a sort of a truth table. And yes, while putting this truth table, actually this part which is written in black is redundant, not required. We can simply have what is written in blue. So each line can represent one memory location, and the subsequent memory locations could be subsequent content at this subsequent location can be written in every subsequent line. So the assumption there would be that the first line means address 0, second line would address second line mean the address 1, the third line mean address 2, so on so forth. So only this content would be sufficient to show what is there inside a ROM. You are saying because it's a read only memory, content is fixed, nobody is going to change the content, it cannot be changed. Because content cannot be changed, so we can write the content in sort of a file or basically an array, and we say that this is the content of my read only memory. Now if we specify the content at each and every address, then it looks like a sort of a truth table. Now I want to design such a read only memory. How do I design it? It looks like a truth table. So because it looks like a truth table, so what I can do is I can create 4 different functions. So I can say that my f0 is actually the sum of mean term 1, mean term 2, 4 and 5. Similarly, function f1 is sum of mean term 1, 2 and 5. My function f2 is sum of mean term 0, 2, 3, 5 and 7. and function f4 is a sum of minterm 0, 1, 4, 5 and 7. So after writing this sum of minterm expressions, then I can use K-map to minimize it and find out what are the functions for corresponding this f0, f1, f2, and I can write them in form of a, b and c. So this way I can design a ROM. So in other words, what we are saying, that for designing a ROM, designing a read-only memory, I can use my combinational circuits. I can use my AND and OR gates to say that yes, this is actually a ROM. In other words, we are also saying that a ROM, your memory cells could be defined by your combinational logic. There is no memory cell. It's a perceived memory cell. If we are saying 0, 0, 0, my output is 1, 1, 0, 0. So we are perceiving that this 1, 1, 0, 0 is stored in some sort of a memory cell, but actually it is coming out of my combinational circuit, or a circuit which is made of AND OR NOT, etc. basic gates. Correct. So but yes, it is not always the case that we always design ROM using this basic circuit. There is also a possibility that we can use memory cells, and if we are using memory cells, then we can design it something like this, that let's say we have these memory cells where the content of all from 0, 1, 2, 3, 7, 0, 1, 2, 3, 4, 5, 6, 7. So whatever is the content that is stored in these memory cells, and we can then access it using a multiplexer. So output of each would be given to multiplexer, and the 3-bit address ABC will go here, and output would be F0. Similarly, we can have the memory cells for all other F1, F2, F3, F4, and the total number of memory cells would be 32, and corresponding memory cell will go to 4 different multiplexers, and F0, F1, F2 and F3, 4 outputs will come. So this is also a very commonly used design of a ROM using a memory cell. Now, if this is how we design ROM, then what would be the memory cell looks like? Now, there are various possibilities for these memory cells. One of it is called programmable read-only memory. Programmable means that whether 0 need to be written or 1 need to be written, so this 0 or 1 is written at by passing some, let's say, a very high current, or it may be a fuse, which says that if it is short circuited then it is 1, if it is open circuited then it is 0. And using that short circuit and open circuit analogy, so there could be like a high current will pass, and then if material is of low resistance, it will burn out, so the fuse will go away, so it will become open circuit, and otherwise it will remain short circuited. And in usual operation, the current rating would be less, so it's programmable. But once programmable, you cannot change it, and that's anyway the definition of ROM also, that read-only memory, you cannot change the content. But one thing that if content cannot be changed, it is highly unusable. So if you cannot change the content of read-only memory, you can never ever change the content of read-only memory, and you can only change at the time of designing or at the time of fabrication. Then what is the use of such ROM? The use would be there, but it would be very, very severely limited. So that is why in last 30-40 years we have developed, or we have thought about various techniques so that it become programmable and it's easy to program. So one of the other technique which is used is called electrically erasable programmable read-only memory. So that means using some high current or high voltage, we can erase it also, and then we can program it again using some high voltage or high current. So that means every time you would like to use that ROM, then you can program it. The other methods, whatever storage types you have magnetic storage. The hard disks are usually magnetic storage, or your DVDs or CDs, they're all optical storages. They're also sort of ROM that once you have written in your optical drive, that's why it's also called CD-ROM, compact disc read only memory. You cannot write it again and again. So but once you have written, then you can read it. Although now we have techniques to and these techniques are cheaper, that you have these laser pointers which will be able to write to these optical methods also, and you can read also. But usually reading is much faster than writing you do once in a while. And also all the ROM cells which are writable, total number of writes are also very very limited. So let's say each location you can write only, let's say 10 number of times, or 1000 number of times, or 100,000 number of times. The last option which is given here is flash. So you have these USB sticks. So these are called NAND flash or NOR flash. So all of them are also sort of read-only memories, and you can write them, but once you can read them multiple times, but you can write only some finite number of times. The value will remain there. Okay, so now these read-only memories, you can see that I can use it to design any combinational logic with n variables. So we see that I can design a ROM by creating m functions of log n variables. I want to design a read-only memory of size n cross m, then I would require m functions, and each of these m functions would have the variables which is equal to log n. And on the other side also, if I have a read-only memory which has which I want to use to mimic a combinational circuit, which is also possible. So let's say I want to design a combinational circuit with n variables and m outputs. So I can do it. I can design a combinational circuit without using gates. I can design it using a ROM. The size of that ROM would be 2 to the power n into m. So these many number of entries in the truth table, and because each entry would have these m bits, so m functions would be possible. Okay, so this gave us a little more idea that if I want to create a generic method, the original question where we started with this lecture, that can we design a circuit which is generic enough and which can use to design any function of, let's say, 4 variable. So then what we can do is we can use a ROM. We can say that this particular ROM will have 2 to the power 4 16 entries, and because this function has only single output, so 16 cross 1, that many number of entries are there, then we can implement, or we can say that this particular function would work like this. So in other words, this ROM can be used to design any generic combinational circuit with n variables, m outputs. So this is one method which can be used to design programmable logic. Further, we can use EEPROMs, electrical erasable, so that we can reprogram them by passing high voltage, high current, and some controllers. We can use flashes, we can use other methods to have these read-only memories, and which is programmable as well. Okay, so this is one method of designing programmable chips or programmable hardware. Now all these programmable hardware devices or logic devices, they are typically called PLD, programmable logic devices. They are various in nature. Different type of programmable devices are there. All of them are programmable, but by different means. there are various examples, so we'll see a couple of more here other than memories, so other than ROMs, because ROM would have certain challenges. So yeah, we can have PLAs, programmable logic array. It could be CPLD, complex programmable logic devices, or FPGA, field programmable gate arrays. So we'll see all of these one by one. So in PLA, what would happen? PLA is a standard AND OR combination. So we have seen that any n input logic can be designed using two level logic, sum of minterms, or we can say sum of products. Now what is this product? Product means it's a AND gate, and sum means it's a OR gate. So here in this programmable logic array, there are k AND gates. Okay, and all of these AND gates are connected to these n input wires, and actually 2n. So because each input would be available in original as well as complemented form. Okay, so such k AND gates would be there, and all these k AND gates would be connected to my m output lines, or basically m OR gates would be there. So each OR gate can be connected to any of these k products. Depending on which OR product it is connected to, it will create different function. So effectively, we would be able to create m different functions, assuming all of them are using same n variables. So some of you were asking and thinking that why we are taking inverted as well as original input as available. So it's primarily because of this programmable logic array. So in early 80s, when people have started thinking about programmable logic, then they came up with this idea. And in this idea, so because the cost of inverter was used once, so what they did, that whatever n input lines were there, they created the inverted of these n input lines also, and assumed that in the AND array all of them are available as an input. Now each of this AND gate can be connected to either the original input or the inverted input. Now which would be the actual lines which it would get connected to? So there are some fuse wires here also, and using these fuse wires, the connections whatever we would like to connect. So let's say out of this there are three inputs A, B, C. So out of A, B and C, we would like to connect one particular AND gate with A and B bar. So although there are 6 inputs which could be connected to AND, this one particular AND, but only those two would be fused, otherwise rest would be open circuited, they won't be connected. So similarly, there would be k such AND gates or k such product terms, and using those k product terms, again there would be fuse wires here. It would choose that which particular value should be connected to each OR gate. Now what should be the value of k? Ideally it should be equal to 2 to the power, so if there is n inputs, there should be 2 to the power n product terms. Okay, but because of optimality, it is usually kept below 2 to the power n, so that because not all the product terms would be required in all the functions. Okay, so this is how programmable logic array works. So it's a generic AND and OR array gates, and the fusing is, or basically connections is done using fuse wires. Now the next one is CPLD, complex programmable logic array. So after they have designed, after people have designed PLAs, so they wanted to make something more complicated. In PLA, you can have an input and one function. So the output of this function cannot go to some other as an input to some other function. So basically this is the intuitive idea behind CPLDs. So in CPLDs there are multiple function blocks. Each of these function block is actually a PLA, and there is the interconnection array. So in this, because of this interconnection array, the output which came because of one function block can also be given as an input to another function block. So using this, what you are effectively able to do, you are effectively able to create a multiple level logic, or a logic where output depends on not only the inputs but also the processed inputs. This CPLD is coming from a company called Xilinx. It is its name is XC9500XL, high performance CPLD. So this is a family, which means that there could be multiple specifications, number of macro cells could be different, number of registers, number of input, etc. could be different. So the overall architecture, overall design of the CPLD is there are 4 function blocks, and in each function blocks there is a possibility of 18 micro cells. Each macro cell means one PLA. Okay, so and there could be 18 outputs of that PLA. So which essentially means that you have you have 18 outputs, and number of inputs are also 18. Now it's written 54, then why am I saying 18? Because it is 18 plus 18. Input is available in original as well as complemented form. Inputs are available from here. So from here, this interconnection would be able to give the input to all these function blocks, and there it can again generate 18 outputs. So these 18 outputs are again given back to this interconnection blocks, so that this 18, some of them can also be given as an input to other function blocks. So similarly, all these 4 function blocks are connected. Now I can create more complex logic, which can take all these different 18 inputs, and it can also do some processing in between. From it can pass the output from one function block and it can give it to the other function block. So this way it because it was complex at that time, so that's why it is called complex CPLD or complex programmable logic device. Let's quickly look at these 18 microcells also. So you have 54 inputs, and each of these product of terms are there. So you can have this and or cells are there. So these are the product terms, and after that you have all these or cells which will generate different outputs. So there are 18 outputs which are possible because of this. This was not even sufficient, that the CPLD were able to make something more programmable, but even more programmability was required. So then we restored to something more like which is field programmable, so that we can program it again and again. Field is usually electric field here. So basically this is programmable using electric field or voltage or current. Now here you call it gate array, because there is some basic logic which has been repeated again and again. So here the basic unit is configurable logic block. People call it different with different names at different proprietary hardware. So but the idea is that some particular cell is created which has been repeated again and again, which has been used again and again. So this logic cell, also called configurable logic block, will usually have some memory lookup table inside it, and there will also be a programmable interconnect, so any other CLB can be connected to the other CLB. So this is another way of programming a logic, or a logic which can be programmed using FPGA also. A typical CLB looks something like this, that let's say there are 2 lookup tables. So lookup table is essentially combination of your memory as well as your multiplexer, so that it takes 4 input, but it stores the output. So whatever is the content of LUT, so let's say if it is 4 input and LUT, then there would be it would internally have 16 cross 1 memory. So that 16 cross 1 memory would store the truth table content of a function which you would like to execute, plus there would be a mux which would give output as one of them as output based on whatever is the input. So this is one CLB block which has two LUTs, and these two LUTs has both of them has 4 inputs, and there is a mux here, so it can have like 2 or 3 different outputs. So this CLB can be used to implement two functions of 4 input each. It can also be used to create 5 input functions, so 2 input from here and 1 input from here. So 5 input functions can be used, can be created using this CLB, and some selected 9 input functions are also possible to be created from this CLB. So the idea is that you will feed the content of your truth table in lookup table, and this in the memory, and this lookup table will give you the output corresponding to one function, whatever we would like to design or program. Okay, so this way these FPGAs can also be used as a programmable logic. Now with this we will close this lecture, and we will learn about this configurable logic block. Once we had we will also see how the sequential logic will work, and then we will have one more lecture explaining how this programmable logic can be created. So in summary, what we have done in today's lecture, we have seen how a programmable logic can be created using generic combinational circuits. So we have seen 4 methods: read-only memory, PLAs, programmable logic arrays, CPLDs, as well as FPGAs. So any of these methods can be used, but as we are going more and more complex, so these days mostly FPGA is used as a programmable hardware solution. Thank you very much.